Just going to look at a couple of, like 2 or 3, I think it's 3 questions I've got there. Different HSC questions that appeared over the years. This one's nice because it's actually an example of variable angular velocity, which at the time people went, hang on, you can't ask that because this course has constant angular velocity. But it is still a constant angular velocity question if you look at it closely. So what we have is a train going around a circular track, radius 8 metres. The train's travelling with a constant angular velocity. But what they want us to eventually work out is we'll find the phi to t. The way that phi changes will be variable. So when we go to a different reference point, the angle that's swept out there will become a variable angular velocity. So that was basically the idea behind it. So they've set our question up. Let's see the first part of the question. First part of the question is to find the theta to t. It's all right. We know that L is a theta, length of the arc idea. So dl to t would be a times the theta to t. Now, dl to t we were told was u, that was the constant velocity. So u is a to theta to t, we just simply get the theta to t is u on a. Really, I suppose we're just doing v equals r times omega, but they're just using different symbols when you think about it. We've got, what are we using? A for the radius and u for v, just to try and confuse it all. Look at this beautiful thing. So now we're going to come up with this expression for the phi to t. So the theta to t, yes, that's going to be a constant because u's a constant and a's a constant. So yes, it is constant angular velocity, but when we put it in reference to how phi is changing, that is not constant. So we've got to come up with this expression, but they've given us a hint. We've got to show a sine theta minus phi minus x plus a sine phi is 0. So, okay. Well, if I play around with the triangle so I can work out some of the angles, because where is this angle theta minus phi that they're referring to? So exterior angle of a triangle, I can use that idea, and we get that its angle NTO would be theta minus phi in our diagram. Well, then I just apply the sine rule to that triangle. So A over sine phi would be a plus x over sine theta minus phi. Cross multiply, bring everything to one side, and we've got the first expression that they've asked us to show. It's actually just a sine rule question. The tricky bit's the next bit, of course. Now we've got to find the phi to t. Well, I'm going to differentiate with respect to t. Now, if we have a look at it, there are no t's there. So obviously I've got to use implicit differentiation, chain rule, call it what you will. So the variable here is the theta minus phi, that's what's changing. So I will differentiate it with respect to theta minus phi, sine goes to cos, it would be the theta minus phi to t. But remember our laws were if I want to differentiate x plus 2x to make it trivial, I could differentiate x, then I could differentiate 2x, add them together. So it's the same idea. I'm saying, well, yes, I could differentiate theta minus phi. Well, what I'm going to do is I'm going to differentiate theta and then minus differentiate phi. It makes it a little bit nicer. So I've got theta minus to t minus the phi to t. The second the second term, phi is the variable. That one's a little bit easier. So differentiate it with respect to phi. I get a plus x cos phi, but multiply it by the phi to t. So now all I need to do is make the phi to t the subject of all this. Okay. So, now what have I done? I've grouped it all in one step. So I've grouped my phi to t's, everything that's got phi to t together, and there's the one term that has the theta to t sitting over there on the left. Move that over, but you'll notice now I substituted in what we found the theta to t to be. We said it was u on a, so I've substituted that in, and we get it. Voila! So we get u cos theta minus phi, but I'm now dividing by the a cos theta minus phi plus a plus x, and so on. So, okay. So it looked like a really nasty question, and well, I suppose it was, really. the trick, if you want to call it that, is realizing I don't have to write this as d theta minus phi to t. I can break that up into two derivatives there. Okay, so when d phi to t is 0, or show that when it is 0, then nt would be tangential to the track. So there's our diagram there. It might make life a bit easier. So nt is tangential to the track. Well, that means angle OTN must be 90 degrees. Radius perpendicular to the tangent. Okay, so we know NTO is 90 degrees. Well, NTO, remember, that's the angle we said was theta minus phi. So I can substitute it into our expression. Well, I don't really need to worry about the bottom of the fraction, because have a look what happens on the top. I get cosine of 90, and of course cosine of 90 is 0. And so there we go, we've got d phi to t is 0 at that particular point. Part D. Suppose that x was also equal to a. So now we're going to show that the angular velocity when theta is pi on 2 is 3/5 the angular velocity when theta is equal to 0. So let's have a look at the situation when theta is pi on 2. So now that angle at the centre is a right angle. It's a right angle. OT is equal to a, but we said x was equal to a, so ON is not x plus a anymore, it's now 2a. And, well, a bit of Pythagoras, you'll see why I need that in a second, root 5a. Because now I can come up with an expression for cos phi. Reading off my triangle, it's 2 on root 5. And the cos of theta minus phi, but theta is now pi on 2, so cos of pi on 2 minus phi would be 1 on root 5. Okay, if we sub that into our formula that we worked out, I get u times 1 on root 5, and then on the bottom we have a times 1 on root 5, 2a times 2 on root 5. The root 5s all cancel, we get u on 5a. So alright, we know what it is when theta is pi on 2. What happens when theta is 0? If I substrate in, if theta is 0, actually let me go back to the diagram so I can explain that a bit better. So we're now saying theta is 0. Well, if theta is 0, then t now, I guess, is over here at s. But it also means phi is going to be 0 as well. So now let's go back to our substitution. So we get u cos 0 over a cos 0 plus 2a cos 0. Cos 0 is 1. So we get u on 3a. So we're trying to show that that first one we found is 3/5 the second one. So, well, yes, that's 5/3 u on 5a. So another way of saying that is u on 5a is 3/5 of u on 3a. So we've shown what we need. All right, the yo-yo question, the vertical circle. So we do horizontal circles, but this is now spinning in a vertical circle. So a string of length L, mass M, standard sort of stuff. Mass P given a horizontal velocity of magnitude V, begins to move in a circle. So you can imagine we're spinning I always think of it, when you play with a yo-yo, you do that round the world, you try and do it, and you go, and hopefully it gets a nice circle as it goes around. So O is the centre of the circle and so on. Tension up the string. So for part A to D, we're being successful and our yo-yo is going in a circle. We have to show the tangential acceleration is given by this wonderful expression over there. All right. Well, we know S, because they've used S there, right, just to make it really confusing, instead of calling the arc length L, they've called it S, and instead of calling the radius R, they've called it L. But so S is equal to L theta for this problem. So the velocity, so the linear velocity, will be ds to t, which is, of course, L times the theta to t. Once again, it's just our v equals r omega, but using different pronumerals. Okay, so I want the second derivative, but it's the linear second derivative, the one along the tangent. So it's the derivative of velocity that I'm trying to find. Basically, what I'm going to do is the same as I did when I proved d dx of a half v squared. Same sort of idea. I'm going to rewrite it dv to t as dv to theta times the theta to t. Well, the theta to t is v on L. I can substitute that in. And I get dv to theta. So I have 1 on L dv to theta times v, but then v I rewrite as d dv of a half v squared. The dv's cancel, if you like, and we get our 1 on L d to theta of a half v squared. Alright, we have their expression. They want us to show that the equation of motion is that. There's Bob. I've rotated the problem to make tension look like it's a horizontal force. So now gravity is going off at an angle. And I'll have a component of gravity. Now remember, it's moving in a vertical circle, and we're assuming for this part that it stays in that circle. Vertically, we'll have mg sine theta going down, and we'll have the tangential acceleration as the resultant going up, if you like. Well, there it is. Because ms double dot was the tangential acceleration that we proved in part A was 1 on L d to theta of a half v squared, and by resolving our forces, in fact, what looks horizontal at this stage doesn't come into play. It's really, I'm just looking at the one that looks vertical, which was along the tangent. So it's minus mg, cancel the m's, and we get what they want. Voila. All right. Wow, deduce that capital V squared is little v squared plus 2gl 1 minus cos theta. Okay. 1 on L d to theta of a half v squared is minus g sine theta, and we have to get to that expression there. So d to theta is minus gl sine theta. Half v squared will be gl cos theta plus a constant. So I didn't do it as a definite integral this time. I'm going to find the constant. V squared is 2gl plus the constant. We know that when theta was equal to 0, they told us that velocity was capital V. So my constant turns out to be v squared minus 2gl. So sub it in, and we get the expression that they're looking for. Okay, so the questions are just pretty much the same sort of questions. They're just making it look complicated by throwing extra pronumerals in, changing the situation up a bit. So explain why T minus mg is 1 on L mv squared. So that comes back to the other force diagram that I drew. If we look at the ones that look horizontal, then tension, remember, was going to the left, and we had a component of the gravitational force going to the right. The resultant force would be going to the left, because the way I've drawn that diagram, that tension, remember, is along the string. Along the string is going towards the centre, and the resultant force of circular motion is always going towards the centre. So the resultant force here will in fact be the centripetal force, the 1 on L mv squared. So we get our resultant force is T minus mg cos theta. And that's what I was just saying. The resultant force would be centripetal. So mv squared on L is T minus mg cos theta. T minus mg cos theta is 1 on L mv squared. Okay, so that was parts A to D. Remember, they said we could assume it's travelling in a circle. So now part E. We're going to suppose that V squared is 3gl, and we want to find when tension equals 0. Tension equals 0. So let's sub it in. Now, we just worked out in part C it was that V squared was capital V squared minus etc, etc, etc. So I'll sub that in. But capital V squared, we've now been told, is 3gl. So I'll sub that in. Tension we're making equal to 0. So, okay. We basically got to make theta the subject of this. So playing around with it. Almost there. There we go. Cos theta is minus a third. So, well, I've put it in radians. 1.91 radians, or 911 it is, 1.911 radians. Okay. So now, and I know you love this bit, describes what's happening. Well, what happens when tension is equal to 0? Right, the string's no longer tight, so it's no longer going to move in circular motion. But what sort of motion will it now move in? So you reckon it's just going to drop? Nope. Projectile motion. It's got to be projectile motion. So, okay, so at t equals 0, it's going to go in a projectile motion. So at that point, it's no longer going to travel in a circle. It's going to travel in a parabolic arc. Now, I don't know how much detail they wanted, but I thought, well, what the heck, let's work out the velocity. So subbing all the information in, we know tension was equal to 0, cos theta was minus a third, so there's the velocity it'll be projected at, roots GL on 3. And here's a picture to try and describe what happens. So we're starting at the bottom, we're spinning it, it gets to a point where the tangent is at, what was it, 1.311 radians, but now it's going to shoot off like a projectile. But at some point, the string's going to come tight again, because it's still attached to the string. And at that point, it'll go back into circular motion. And so it'll be like a wobbly circle. And so that's what our particle does. 2003, projectile motion, but with air resistance. So in reality, it's not a perfect parabola, because you do actually have resistance in the opposite directions of motion. So what that means is horizontal acceleration is not 0 anymore. It now has resistance in the opposite direction, and to save us time, they've told us the equations. So it's minus k v dot, and vertically it's not just g, it also has resistance in the opposite direction as well. But yes, make sure you read what's in the parentheses. Okay, how much time we got? Oh yeah, make sure. Derive the expression. So at least they've given us the answer in case something goes wrong and we can't work it out, we've got it to use. So dx dot dt is minus kx dot. I did it as a definite integral this time. So t will be minus 1 on k. Initial velocity is still u cos alpha, that doesn't change. It's a log function. Sub in x dot minus sub in u cos alpha. We're trying to make x dot the subject. So t will be minus 1 on k, make it all one log. Use our log laws. Minus kt exponentialise, and we've got it. So there's actually our vertical motion. So go to physics now and say, you know about this projectile motion? You know how you said horizontal velocity is constant? Oh, no. Horizontal velocity is actually u e to the minus kt cos alpha. All right. They're not going to ask us to derive. Oh, by the way, they're not going to ask us to derive this. They just want us to verify this. And this is where I really wish I'd read the question, because I derived it. Well, so dy dot dt is equal to minus ky. Again, I'll do it as a definite one. It's a log function again. Sub in. I mean, it comes out all right. Eventually. And there we go. Because they gave me the equation and they said verify, I suppose all I've got to do is differentiate it and show it satisfies the acceleration equation that they gave me. Okay. Oh, but, see, the other part of this question says it satisfies the initial conditions. So I guess by deriving it, and I've used the initial conditions, that verifies it. If you had just subbed in, you would also have to sub in the initial conditions to show that, yes, they also work. Find the value of t when it reaches its maximum height. Well, the rules don't change. Maximum height is when velocity is equal to 0. So I'm going back to... Happy accident, but I've got a formula for t because I was deriving it over here. So I'm going to go back to my third one where I've got t equals minus 1 on k log, etc. If you'd done it by substitution, then you'd have to derive this formula. Use sine alpha to 0. So subbing in. And, well, yes, it's an ugly expression, but it is what it is. There it is, T1 on K log Ku sine alpha plus G on G. So what is the limiting value of the horizontal displacement of the particle? Remember, we've got this velocity equation. So dx dt will be u e to the minus kt, etc. I want the limit as t approaches 0 of that integral. E to the minus kt going from 0 to infinity. Well, if you integrate e to the minus kt, you get minus 1 on k e to the minus kt. Now that's a lot easier. Now that I've subbed in, I can see, well, as t approaches infinity, the only spot I've got it now is in that minus e to the minus kt. And we know that backwards exponential, that's going to go towards 0. And so there we go. There's our limiting displacement for our projectile motion. Okay, so handful from Cambridge, and then some from Patel.